Hello everyone, my name is Isa Al Khaldi, and today I'm going to explain about um, the three slides that I'm involved to explain. These are the three slides. So I will I will explain the gas turbine basics. So in the gas turbine section, it displays a part of the turbine containing blades. As you can see, here is the blades. It's also here, and made using creep resistant and directionally solidified DS and single single crystal structure, which is SC. We can call it SC. These techniques are derived from the world of aircraft turbines, but here we are talking about specifically the gas turbine. So what is DS? I'm not gonna be too long in explaining because we have a lot of things to talk about. But in summary, creep-resistant materials are designed to withstand deformation under continuous stress at high temperatures, while directionally solidified materials have a control on microstructure alignment that enhances their mechanical properties, including creep resistance, making them suitable for demanding applications in aerospace, aircrafts applications, power generation, and gas turbine and other high temperature environment. So now we know what is a DS. Let's talk about the SC, or the single crystal structure. Single crystal turbine blades used in high performance gas turbines and jet engines. The crystal structure is without grain boundaries. This design enhances creep and fatigue resistance, high temperature strength, and thermal stability. Fabricated from nickel-based super alloys. So we have nickel. It's mostly made of nickel. SC blades are manufactured using specialized directional solidification techniques. By eliminating grain boundaries, the SC blades offer superior mechanical properties important for withstanding the extreme temperature, which can exceed 1000 degrees Celsius. Their application in turbine sections improves engine efficiency. So we have the efficiency. So we can say efficiency. It can improve efficiency, as well as the reliability, which can make it like last long. And also durability. You know what durable means like durable, like it's a very good material, like doesn't break or deform easily, making it vital and important components in aerospace and power generation industries. So here we have also thermal barrier coatings, TBC. But what is TBC? In the slide says employed to protect aerodynamic surfaces and materials from corrosion, oxidation, and erosion. That is true, but I'm going to talk in more deep about it. So TBC, or thermal barrier coatings, are advanced materials applied to turbine components in gas turbines and jet engines to protect against high temperatures, corrosions, erosions, and etc. Typically composed of ceramic materials like yttria, stabilized zirconia, and others. TPCs provide thermal insulation, reducing heat transfer underlying metal substrates. This insulation allows engines to operate at higher temperature, enhancing efficiency and performance. So again, we have efficiency here, improving efficiency, withstanding high temperatures, and protect against corrosion. TPCs also, as I said, corrosion resistance and thermal shock protection. Important for aerospace and power generation applications by making thermal stresses and observing the thermal stresses and extending operational limits. They play also, TPCs play important role in improving engine reliability and durability. So here also we have more reliable, we say, more reliable. Okay. And more durable, we say, more durable. So now we know what TBC stands for. We know what TBC is. We know what's made of. We know its application and everything. So now I'm gonna move on. Turbine nozzle with TBC cooling air exit holes. So the turbine nozzle equipped with thermal barrier coating and equipped with holes for the outlet of cool air. This nozzle works efficiently to direct hot gases toward the turbine and cool them as well. So it cools the turbine blades. But now I'm gonna focus on the turbine nozzle specifically. So what is a turbine nozzle? Turbine nozzles in general are components in gas turbines and jet engines that control the flow of hot gases to extract energy and drive the turbine blades. They also accelerate and direct the flow to optimize energy conversion. It's also typically located between the combustion chamber and the turbine stages. We are gonna move on the next slides later on, and we are gonna see the whole gas turbine, and I'm gonna talk about it specifically later on. Here is the turbine. I'm gonna talk about it specifically in this slide, but I'm giving you a general idea about it. Also here we have also the turbine in here, the turbine row assembly. Okay, excuse me, just let me erase to make it clear for the one who will watch the video. So the turbine row assembly, it's like assembly of turbine rows with excuse me, with installation of turbine blades excuse me excuse me on a rotor disc, and you can see the holes for the outlet of cool air for cooling the turbine blades. A turbine row assembly comprises turbine blades, nozzles, and associated with components arranged in a sequential fashion within a gas turbine. It forms a critical section where energy extracted from high temperature gases drives the turbine to produce mechanical power. Blades and nozzles work in tandem to efficiently convert thermal energy into mechanical work. The assembly design and arrangement optimize energy extraction and ensure uniform flow distribution. Materials like, as I said before, nickel-based super alloys and advanced coatings are employed for durability, as I explained before, and to make the performance under extreme condition working very well. In the next slide, I'm gonna talk about more about the gas turbine basics. So moving on this slide, the gas turbine basics. Here is the gas turbine assembly. Let's put the sections together. The basic gas turbine machine. So don't worry about the thing in the slide. I'm going to explain in my way everything. So here we have a compressor, and here we have the here is the, let's say, the compressor. Here we have the combustor, or we can call it combustion chamber. And here we have the turbine. So a gas turbine, let's talk about the gas turbine, the whole thing. And then I will focus on each part here. So the gas turbine is a complex system comprising several vital components, each playing important role in generating of power. The compressor here, the compressor is responsible for drawing an ambient air and compressing it to high pressure. So we have air goes in, then air goes in, then its pressure is applied to it. Then it's also typically consisting of multiple stages of rotating blades and stationary vanes. The compressor progressively increases the air pressure, and also we have not only pressure increases, but also we have temperature increases. As it moves through each stage, preparing it for combustion. preparing it for here. So in the combustor, the high pressure air from the compressor is mixed with the fuel. So here we have, let's say, fuel. Okay, we have fuel is injected inside and mixed with air and ignited. So ignited. This combustion process generates high energy also. High energy gas flow with significantly elevated temperatures. The turbine section extracts energy from the hot gas flow to power the compressor, and in many cases an external load such as electrical generator, because this is connected to generator. Or aircraft propulsion system. It can be anything, any type of generator. The turbine is composed of multiple stages of blades that expand the gas, extracting energy as it flows over them. Surrounding these components are the casing. So surrounding each component we have a casing designed to provide structural support, facilitate airflow management, and contain in the combustion process. These casings are often constructed from advanced materials and incorporate cooling systems to withstand high temperatures, like nickel, for example, and mechanical stresses, while ensuring the efficient and reliable operation of the gas. So if you're gonna ask me, for example, the casing, it's made of high standard materials to withstand heat and everything. The excess energy from the turbine shaft is used to operate pumps, compressors, or even electric generator through the output shaft. This output can be from the cold side or the hot side of the turbine. And it's 60 or 70% of the turbine section power output used by compressor. The remaining 30 or 40 available, such as true shaft turbine power, typical normal 50 megawatt single the single shaft turbine gas produces 150 megawatts in the turbine section. So I hope I explained this slide in a short way, so to not make the video too. So moving here to this slide, okay, so moving to this slide again, gas turbine basics. Here we have the F-class gas turbine assembly. We have two sections. One is the top half removed. The second one is the longitudinal assembly drawing, which is this. And we have here the top half removed. So this side, the top half removed, reveals the internal part of the turbine after removing the top section. So here the top section, imagine this is the turbine. The top section has been removed. The multi-stage compressor can be seen. See, you can see the multi-stage compressor. It can be seen with variable inlet guide vanes. You can see the vanes that direct and adjust the airflow into the compressor. We also see the multiple combustion chamber containing swirls that enhance combustion efficiency, and the multi-stage turbine section consisting of rows of turbine blades arranged to convert the thermal energy of hot gases into mechanical energy. So, as I just said, the multi-stage combustor, we can see it here, how many stages, and and also additionally to that, the bottom part of the image shows the exhaust diffuser that distributed gases after exiting the turbine. Now we're gonna move on to the longitudinal assembly drawing. The longitudinal assembly drawing of the gas turbine shows detailed internal parts and how they are assembled together. The precise distribution of different parts like the compressor, combustion chamber, and turbine can be observed, as well as the connections and bearings that support the smooth rotation of moving parts. The lines and connections in the drawing illustrate the complete assembly and operation system of the turbine, including fuel flow, airflow, and cooling system that protects the critical parts from extreme heat.